There are two types of situation involving electricity that you should know about. The first is when charges get stuck and they can't move and they can build up in one place. That is electrostatics. The other is when you allow them to move, perhaps by looping a conductor so that there can be a flow of that charge around a circuit. We're going to look at circuits now and look at the flow of current through a circuit. Before we can begin, we need to familiarise ourselves with basic components that can sit in a circuit and the symbols by which we represent them on paper. I have got a collection of things here, and these are the symbols. The first is a switch. And I have two types of switch here. Both of them, for us, have been encased in plastic to make plugging them in easier. But switches are simply things that can break the circuit, and they can be a press to press on or press to close or such like. The switches can be drawn open and switches can be drawn closed just like this. The next thing I want to show you is a cell. A cell by itself is one of these, and what you'll see on the cell is there's a small plus symbol near the little end that sticks out. The negative terminal of this cell is the flat side. One by itself is called a cell, but together they are known as a battery of cells, or just simply a battery. We have to make sure they're all plugged in facing the same way, and what we're going to find is that this provides the potential difference that will make our electric current flow. Now the symbol for a cell is as follows. It has a large line with a small gap next to a small vertical line. Now the way to remember which terminal is which, and it does matter on this diagram, is to remember that this large line almost looks like a giant plus. And so the positive terminal is depicted as being the large line and a small plus being drawn next to it. This small little vertical line here, if you turn your head on your side, it looks like a negative symbol. So that's how you remember. If you were to create a battery here with 4 cells, you don't have to draw all 4 of them. What you could do is you could miss out the ones in the middle and replace them with dotty lines. As long as you write that this is 1.5, that's 3, this whole thing is 6 volts, you could just say that rather than saying we have 4 cells of 1.5 volts each, we have one battery of 6 volts of potential difference. The next thing that we have that we need to know about is a diode. Now diodes are very strange components. And this one here is really, really small, and it is basically a component that only allows an electric current to flow through it in one direction only. We can get versions of these that give out light. Here is one just here, and you may have used these before. This is a light emitting diode. If you plug it in the right way, it lights up. If you plug it in the wrong way, nothing happens, because it doesn't allow electric current to flow through it backwards. The symbol is a kind of play symbol, or like a next symbol, if you've ever seen that. Now, an important thing about drawing this is if you were to connect it into a circuit with a cell, if you want the circuit to work and you want current to flow, you must draw the arrow within the diode pointing eventually to the positive terminal of your cell. So if I was to connect this with a line here, it wouldn't work because the diode is backwards. The next thing is a plain and simple resistor. Now this is what a resistor looks like when it is without any kind of protection on. It's just a very small little object with some stripes on it that represent the resistance. Here we've encased some of our resistors in plastic because they can get hot and you don't want to touch them. Encased in plastic, you can see it's inside. This is a ceramic resistor, and they do get very hot. They're just depicted as a straightforward rectangle. Lamps are kind of obvious, and we can use bulbs of all different sizes. We plug them in and they are shown with a symbol of an X inside a circle. A fuse is like a resistor. Here's a fuse. This is the sort of fuse that would be inside a plug, and these fuses are there to break if the current gets too high. So when we talk about domestic energy, or domestic use of electricity, what we'll think about is how fuses protect our circuits. The symbol for that is like a resistor, but with the fuse wire drawn through the middle. We've also got devices that take some measurements. Here I have got a voltmeter, which measures the potential difference across a component, and an almost identical looking ammeter, which measures the current flowing through my circuit. More about those later. The very final thing on here is a thermistor, and these can look different depending on what you want to use it for. Here is a waterproof thermistor. Here is a pair of thermistors that are used for various different things. Now we'll talk about these later, but what these basically are is a circuit component that works and allows current to flow through it when it's hot. For our current to flow through the circuit, we have to create a potential difference, and these devices will do that for us. A nice analogy to think of is if you want a ball to roll down a hill, one end of the hill has to be higher up than the other end. It is at a position of higher gravitational potential. What your battery does is it creates one end of your circuit at greater electrical potential than the other, and this makes the electrons flow through the circuit trying to get to the other side. Of course, you could provide a potential difference with a single cell, a whole battery, or with a power source that plugs into the mains. Now this provides various different types of current. This will produce a direct current, and depending on whether or not we have plugged into the direct current terminals of this or the alternating current terminals of this, we can get two different types of current. Direct current flows continuously in one direction, and then alternating current shimmies back and forwards, shoving and shunting the electrons as they go. So I have a bucket here, and it's full of sand. It's going to really help us to understand why current flows and what current is. You see, each individual one of these grains of sand is an electron, and they are in a circuit here. Now, if I had some sand in here and put it in the bucket, it's just sitting there not doing anything. If I want it to flow, I've got to raise one end up to a higher potential than the other. And so what I'm doing is I'm going to use gravity to raise the potential of this sand. Now, in an electric circuit, it's not gravity that does it, but it's the force of repulsion between the electrons themselves. I can raise it to a higher potential and I can start to pour. There it goes. There is now a flow of sand. Now I could have a flow that was very, very small, or I could have a flow that was much larger than that. I would need a way of measuring what the flow was like. What is the rate at which sand was going from here down to there? Now, of course, I could put a little counter in, and my counter is called an ammeter. So here is my ammeter, and we'll put this in an actual circuit slightly later. But what an ammeter does is it measures the amount of electron flow going through it. But here is a little detail. An ammeter could not possibly count every single electron going through. There's just far too many. So the electron counts a whole load in one go. Here I've represented that by having a beaker full of sand. That's one beaker, that's two beakers, and on and on. Now we don't count beakers of electrons, we use a different unit. We call it a coulomb of electrons. 1 coulomb that second, another coulomb that second. I know that I'm putting in 1 coulomb of sand every single second. And so I call that 1 amp of current. And it represents 1 coulomb of charge every single second. Now I've made a circuit. You can see it's a constant loop around which my charge can flow. And I've drawn it here with a circuit diagram so that you can see that this represents this. We have here 4 cells in a battery, and I've drawn the battery symbol to represent it. As we follow the line around, you can see we get to a switch here in the open configuration. Then there is an ammeter, and that tells us quantitatively with a number how much current is flowing through this circuit. It then proceeds through a bulb before going back to the battery. If I close the circuit, the light bulb illuminates and you can now see there is a reading of current. If I break the circuit anywhere, you can see that the current stops. Now, so that you can see, I have here a ginormous ammeter for measuring current. It has an analog scale on the front. And when I turn the circuit on, you can see it reads a steady current of about 1.4 amps. Now look what happens when I disconnect it from this point in the circuit and instead I connect it after the light bulb. So I'm going to move it just over here and I'm going to plug in my light bulb. And what you'll notice is that because of the length of my wires, you'll have to look at the light bulb through the actual ammeter itself. I'm going to turn it on and you can see now my ammeter is connected after the light bulb and you can see it settles at 1.4 amps. You see, it doesn't matter where I measure the current. In a single loop circuit like this, that we describe as a series circuit, the current is the same everywhere. We can use our ideas of a flow of charge to represent current as a formula. And so how I would describe current with word equation is that current measured in amps is equal to the amount of charge that flows measured in coulombs. And remember that what a coulomb represents is like a beaker full of electrons. It's just a very large number of electrons of a scale that we can count. And we would divide it by the time. And we would measure that in seconds. You can see that what an amp could stand for is a coulomb per second. Now, word equations are great. They help you see how the quantities relate to each other, but scientists use a shorthand to represent this as symbols. The symbol for current is the symbol I. And that is because Ampere, who discovered and first talked about current, was French. And he decided to call this the intensité de current. And so I got used instead of a C. So you've got to remember, when you see an I in an equation, it represents current and not anything else. And this is equal to the charge divided by the time. Now time is a lowercase t, that's easy. But what about charge? Now the problem is with using C is it's already used for Celsius, it's already used for coulomb. So they decided to go with something not used. And so they used the symbol Q. That current is the charge divided by the time. And you will see this rearranged in the format that charge can be found by doing current times time, multiplied there in the middle. So if I had 3 coulombs of charge and it was flowing in, let's say, 6 seconds, then you can see that my current would equal 0.5 amps. But that is how we do it.